Okay. Hello students. So today we are going to study wave optics, and you might have already studied about different types of waves: sound waves, material waves, non-material waves, electromagnetic waves, and specifically light waves. So in this class we are going to study about wave optics, in which we will mainly consider light waves. However, the same concept is applicable to other kinds of electromagnetic waves as well. So the first thing about wave optics is a contradiction among scientists, that what is light? Is it a particle or is it a wave? So as you know that in earlier days the science community was highly influenced by the followers of Newton's, and Newton has given the corpuscles theory for light. So according to the corpuscles theory, light is nothing but small packets of energy, or small packets that follow the law of collision, and that's why the reflection is explained by Newton. But later it came out that certain experiments was not successfully explained, but there was no such theory which could define reflection and refraction of light. So there was no basic hard thing to believe whether light is what is light. So some scientists have already stated that light could be a wave, but there was no way to explain that. But later some scientists came out with proper reasons. One of them was Huygens. So Huygens Principle came out. So the scientist was Huygens. I think I don't remember the exact name of full name. So this was some Huygens Principle states that light is nothing but a wave, and the light we see is the sum of, or say the set of several waves, and that wave front is the face of light. Means whenever light travels, suppose there is a parallel light beam, it contains several waves which are moving, and such that their front is like a straight line. So he also suggested that whenever light travels, every point in its direction behaves like another source of light. So consider a wave moving like this. So consider any point in this. So here is a point. Here, this, let's say, name point A, B, C and D. So each point is a wave. From here, each point is a source of wave. So from every point a wave is starting, and you can see a new waveform is forming. So this, wherever the new wave has formed, is a new wave front. So consider when a point, the original source is a point. So consider this original source. Light starts from here as a wave. Obviously it will go throughout and it will move like another wave front will form like a circle around this point. So more or less, this is not a circle, I would say. Obviously light will move in 3 dimensions, so it will be a sphere. Now consider every point on that sphere So for convenience I'm taking only 5 points. So again circle will form here, 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 here and here. So if I join every point that has come so outermost, it is giving me another circle. Why another circle? Because I have just taken 5 points and you can see the flower structure here. If I consider every other point, it will form another of this. Look, let me get it more. So here is the point. Here was the first source. Consider this point, this point, this point, this point. So here I found this, this, this and this. You can see there's a wavefront forming, which is a concentric circle of this. So in this form, whenever a wave is forming from the point, it forms concentric circles around itself, and this you can see in the water wave. Like if you throw a pebble in water, you can obviously observe the concentric circles that are formed. So Huygens principle is very easily explained here. However, this is not a way of proving or disproving a theory, but yes, you can visualize how Huygens would have hypothesized this principle. So in this way you can I would say explain how light travels. So, and this is true for any wave. Like you see that even if you consider a string wave, what happens? First, the point nearest to the disturbance gets disturbed. Like I have pulled it up and down, it disturbs. This makes the front part, this disturbs the point just beyond it. It is starting to move from them, and the same happens to another. What happens? First, I have moved a rope. The rope's first point has disturbed. This disturbed point is disturbing the next point, and the next point, second next point. So this disturbance is being carried out. The same way, what happens in any wave propagation? First, one point is getting disturbed, and the surrounding points are also getting disturbed in the same way that middle point is getting disturbed, and those points are now acting as a source, and they are also disturbing the neighboring points. So every point wherever the wave reaches acts like the source of a wave. So if this can be perceived very easily using an experiment. You can try this. Take a flat, I would say, tray, fill it with water. Now take some long apparatus from your kitchen or something. Like you could take a knife, put vertically like here, and dip in the tray. What will happen? You will find waves parallel to this face, say AB, and in this way you can see the wave traveling from AB to, let's say, AB to DC. Now you could put two distractors, two obstacles here and here. Let me mark it with different colors so that it makes some sense. So I put two obstacles. These obstacles, say one obstacle is P and another obstacle is Q. So they are leaving very small part through which water could pass. But you know that water doesn't travel when wave is traveling, right? So this is only the disturbance that is crossing from here. So what should happen if this much is the opening? Means I would again highlighting it. So this part is the opening. So what should happen? The wave should move like this, means through like this. But if you observe what happens, you will see it happens like this. Means again, let me get a clear idea. From this opening, wave will ideally, means theoretically, if wave travels without making the further point any source, what would happen? The wave would follow its pattern like this. If it has been some kind of photon or some kind of particle, it will simply go like this. This would how wave would have propagated. But what happens? It goes like this. Means earlier it was coming this. It was moving parallel to each other. Now it is making concentric circles because we have a obstacle and where we have a very small opening. This opening is allowing very small part of this liquid or this water to be disturbed, and they are acting like a source. So we are getting something like sectors, or the concentric sectors, or say concentric parts of the circles. So this is only for visualizing how Huygens principle could be shown. Now, what happened when Huygens principle came into publication? First time it was published, and then among scientific community it was highly disregarded, and people questioned its authenticity because there was not much evidence and not much experimental proof behind this principle. So Huygens was not given that much preference, and this principle was not given any value in front of the Newtonian mechanics or Newtonian theory behind light. So what made this any valuable? You might have heard about Young's double slit experiment. I would not say double slit experiment, simply say Young's experiment. So Young was a scientist, and his experiments showed that light cannot be taken as a particle, because the experiment showed some behavior of light which could not be defined according to the particle theory of light. So this Young's experiment, am I writing the spelling Young's right? Yes, Y-O-U-N-G. Yes, Young's experiment was the experiment that proved that Huygens principle had some value. So before going to what Young's experiment was, first let's take an instant whether Huygens principle could explain the concept of reflection, because Newtonian's mechanics or Newtonian's explanation behind light could simply explain how light gets reflected from a surface. Like if you throw a ball on a wall, it gets rebounded, and if there's no gravity, it will rebound following the law of reflection, that is angle of incidence equals to angle of reflection. But if we are able to explain that Huygens principle can also explain the light's reflection, then we can think further about Huygens principle. So let's say how Huygens principle can explain. So first we are considering a ray of light which is falling on a surface, and we are observing its behavior. So we know it is following. So it's not that good. I have just drawn the normal, and with the normal it's making angle of refraction, and you know that angle of incidence I is equal to angle of incidence R. So you're seeing the same is happening with all the three rays that I have drawn. However, you know that there's not only three rays, there are millions of rays, or say million of waves in the light, as we know that light has a behavior of light wave. So when we are talking about the angle of refraction and angle of incidence and angle of reflection, first we have to consider this parallel beam of light. And when we are saying that it is a parallel beam of light, how the wavefront will look like? Wavefront would look like a flat surface. Why a flat surface? Because wavefront is always parallel to the wave propagation, and a parallel beam of light would have a flat surface perpendicular to it. So I would say visualize this way, that one cylinder or one cuboid is moving that way, and it's these lines, means lengthwise are the rays and its widthwise is the wavefront, and it is falling on a surface. So consider this, means what's happening, it is moving forward, its width is coming closer to the surface, and consider this, it has just reached the surface, means this part has reached the surface and this part is still above. So now let's consider the relation between this angle and the angle of angle of incidence. And please let me know if the drawings are not making sense. In further classes I'll try to improve the drawing, and you could also take helps from books to understand the drawings. So here you can see the wavefront and the angle of incidence is making angle of 90 degree. Consider this angle I is the angle of incidence, right? So angle I, and this angle, say X. I'm just taking X, nothing special about it. So relate these angles. So if this is I, we can say this is 90 minus I. And if this is 90 minus I, X is equal to nothing but I, because you know that sum of three angles of a triangle is 180 degree, and this angle is already, we know that this is 90 degree. So we came to know that the angle it is making, the wavefront is making with the surface, is equal to the angle incident ray makes with the normal. That means the wavefront makes an angle equal to the incidence angle, so or angle of incidence. So X equals to I, so I'm considering I only, no X. Now consider what happens when then this end of the front hits the surface. It acts, means any point coming into the light's path is a new source. That's why what Huygens Principle say. So it will start making, means it will start moving from here until this point gets here. So I'm considering this. So again, to avoid confusion, I'm considering wavefront AB was here. So A has reached this point, and So again, consider this A has reached here, so cut this A here and write this is A and B here and ignore this B. Now since this angle I, using this angle I, can we find this length here? You can try trigonometry, right? So for that we can simply say, let's the length of this waveform is L, right? So the length of this part means say AB, or say I'm saying this point as O, no specific reason, just O. So BO is equal to L times, and what is this? This is theta, this is the base, this is the perpendicular for this thing. Consider this way, L is the base, BO is the perpendicular, and this is the theta. So this will be L times tan theta or tan I. L times tan I. So in that time, what would be the from here to here, light is traveling. Suppose this is any kind of light, it could be any kind of medium, just taking the speed of the light as v. This is not, we are not taking c. So the time taken is t equals to L tan I by v. Now in that duration here, this a circle will start forming at A. Consider the point A. Here we'll have a sphere forming, or say circle forming. We are considering 2D for convenience. So at this, when this point is here, this would have formed a circle, because it is moving with the same speed v. It will make another vt of radius, circle of radius vt. Let's say vt would be something like this, while this had just dropped. So you can simply say that the new wave front would nothing but the tangent here, right? So let's say it like this, tangent. Now consider again this thing, this vt, this is the distance, radius vt is same as the distance vt. We had no need to take L tan I, something like that. We could simply say this as the distance traveled as d, and this is also d. So d by t, this distance is d, v2 is d, considering this d. If you consider these two triangles, we have d equals d, we have base equals base. We know that sorry, what am I missing here? Yes, one thing, this angle is, these two angles are 90 degrees. So by which side angle side, by the theorem of side angle side, we can say these two triangles are what do you call, congruent. So by congruency we can say that this angle here is equal to I, and again we are saying that this is the wave front, so this would be the reflected ray, right? So this angle is equal to the angle of refraction. So we are getting I here, so that's why I equals R. We are proving this thing using the congruency theorem, and this is how you can prove it. There could be several other ways. You could put real calculations like 3 centimeters here, 4 centimeters here, the angle comes out to be 20 degree, here is also 20 degree. Using that you can prove it. So this is how Huygens principle explains explains light's reflection. Now it's time to explain light's refraction. Let's see if Huygens can explain that. So first, recall what is about refraction. So you know, whenever light travels from one medium to another, it bends at the interface. And what does that mean? So this is medium 1, this is medium 2. This might not be visible, but remember, this is medium 1, this is medium 2, and this is the interface that is dividing the two mediums, and light is coming from here to here. Let's draw it. So this is the light wave. I'm considering single ray. Again using black to draw the normal, and it bends. Why? This is the concept of refraction, that whenever light travels from one medium to another, a light ray bends at the interface, and this bending means it will bend towards the normal, it will bend towards away from the normal. It will depend whether medium A is denser than medium 2 or medium 2 is denser than medium 1. So first, if medium 2 is denser than medium 1, the light will bend towards the normal. As you can see, light has bent towards. Earlier it would have gone straight this way, but it has bent. If medium 2 is rarer, it would have bent this way. Now what is rare and what is dense? Rare and dense medium in terms of light is nothing has to do with the solid state or liquid state or density or something. It has to do with the speed of light. In a medium, suppose one medium is rare compared to another medium who is dense. So let's consider a medium P and medium Q. So medium P is rarer as compared to medium Q. So we can say that speed of light is more. In where? In medium P. अगर स्पीड ऑफ लाइट किसी मीडियम में ज़्यादा है तो वो रेयरर मीडियम है, और जिसमें कम है वो डेंसर मीडियम है. ये बहुत आसान है समझना. अगर आप एयर में ट्रैवल कर रहे हैं, सपोज जैसे सड़क पे वॉक कर रहे हैं, तो हम एयर में ही तो ट्रैवल कर रहे हैं ना. सड़क के ऊपर चल रहे हैं लेकिन हमें क्रॉस तो एयर को करना पड़ रहा है. उसमें हम आराम से चल सकते हैं अपनी स्पीड से, लेकिन अगर वही हम पानी के अंदर चलना हो, सपोज जैसे वेडिंग इन वाटर, पानी में टहलते हैं कभी कभी हम स्विमिंग पूल में, मज़ा आता है गर्मी के दिनों में, तो इन दैट केस आवर स्पीड इज लो. सो you can say that air is rarer for our traveling as compared to water. In the similar way, this is a coincidence, don't take it कि जिसमें हम आराम से travel कर सकते हैं उसमें light भी आराम से travel कर सकती है. So in the medium in which the speed of light is low is denser, where the speed of light is more is rarer. Now consider it in context of vacuum. Speed of light is believed to be fastest in vacuum, that you know is given by c. that is very close to 3.0 into 10 to the power 8 meter per second, and this is also almost the speed of light in air, but speed of light in air is not exactly same as speed of light in vacuum. It is slightly less. So in comparison to vacuum, the medium air is slightly dense. Similarly, if with compared to air, water is dense. With compared to water, glass is dense. With comparison to glass, diamonds is dense. So we have to consider that how this bending is taking place and how we can explain this using Huygens principle. So first, before going into that, let's come to Snell's formula. Are you remembering that? I hope you should, because Snell's formula gives a concept of refractive index. I think here refractive index is given by eta. No, this is given by mu. Mu is equal to sine I by sine r. So what is mu, what is I, what is r? Sine I, here I is the angle of incidence, here r, which could be, means I'm not considering this wave, this ray, remove it. I'm considering medium 2 is quite denser as compared to medium 1. So I is less than r. Sorry, did I say that? I is more than r, because this ray has bent towards the normal, so r is the smaller angle here. So you will come to know that sine I by sine r would have some value greater than 1. So whenever you get mu greater than 1, you can say that light has traveled from medium 1 to medium 2, and medium 2 is denser than medium 1. Means light has traveled to a rarer, to a denser medium. Similarly, if you are getting mu smaller than 1, then you can say that light has traveled from a denser medium to a rarer medium. And I hope you remember the basic concepts of Snell's law. I'm just reminding you here, so I'll not going deep into Snell's law and going into Huygens principle, how Huygens principle can explain refraction and Snell's law at the same time. So again, I'm considering an interface. Earlier I was considering a reflecting interface where light was getting reflected. This time I'm considering a refractive interface. So this could be something transparent, right? Like a glass, like a water interface or something. Water that should be still. It is not moving much, so that light is not getting disturbed here. It is getting proper refracted inside without much diffraction. Again, I'm considering a wavefront, like a rectangular wavefront. It is coming like this. Our AB has come from the space, or say obviously sun से आ रहा है ये लाइट, आ रही है ये लाइट, और ये हमारी लाइट ये यहाँ है. Now I'm considering the wave of light to be of speed c in air, or say, don't say c, simply say v1 in air and v2 in water. This is a air-water interface. Simply write that down to have any confusion. I hope this is visible to you. Yeah, I think this is quite visible to you. So at every point, again, you know that light in every point in the path of light will behave as a source of light. So you know, when जब A यहाँ तक पहुँच चुका होगा, B कहाँ होगा, यहाँ पे. और अगेन हम इसको क्या कंसीडर कर रहे हैं, इसको D कंसीडर कर रहे हैं. यहाँ पे से ये V2 बनाएगा, राइट. V2 के स्पीड से बढ़ रहा होगा. सो जब तक ये फेस, यानी ये पॉइंट B हमारे वाटर सरफेस को टच करेगा तब तक ये डी बाई कितना टाइम पास कर चुका होगा, d/v1, बिकॉज लाइट की स्पीड v1 है इस मीडियम में, जो कि जिसको हम एयर मान रहे हैं। तो यहाँ पे जो लाइट सोर्स है, जो नया सोर्स बना है, ये पॉइंट, वहां से लाइट कितनी दूर निकल चुका होगा। सो द डिस्टेंस ट्रेवल्ड बाय लाइट एट द टाइम व्हेन दिस पॉइंट हैज टच्ड हियर would be time taken into the speed of light in this medium. So d divided by v1 into v2. So what will we do? We will make a circle or semicircle of this radius. So would be something like, and you know कि ये डेफिनेटली इस d से कम होगा क्योंकि स्पीड एयर सॉरी I'm considering v1 here, speed, v2 here. Because the speed of light in water is less than speed of light in air, so I'm considering this whole thing as d dash. Now again consider यहाँ से जो नया वेव फ्रंट बनेगा वो कैसा बनेगा। उसके लिए हम एक टेंजेंट बनाते हैं। ये आया हमारा नया वेव फ्रंट। सो लाइट कुछ इस तरह से ट्रेवल होना शुरू होगा। लाइट, डू यू ऑब्जर्व द बेंडिंग? Here it was moving like this, now it is moving like this. It was similar to the structure that I had shown here. Light was moving to an angle. Now this angle has decreased because the light has bent towards the normal. Again, what I would do, I would show how normals are here in our new diagram. You could see that this is the normal and this is the normal. If we are considering two rays, ray 1 here and ray 2 here, we could observe the bending of rays. So bending of rays is quite observable here. What about the Snell's law? Can we say that Snell's law is valid by explaining through Huygens Principle? I would say yes, because I have already studied it. Now it's time for me to explain this to you. So to find the angle, we know that by previous experience you would know that the wave front is making an angle with the interface is the same angle as the angle of refraction here, that is r. So we know this is r and we know that this is I. Now consider I is what? If we are considering sine I, what is sine I? Sine I is d by this length. Let's consider, this time we are considering this L. Okay, so this time we are considering the length of the interface on which the wave front has fallen. So this hypotenuse is L. So sine L equals to d by L, and sine R. Sine R is equal to d dash. This length is d dash. D dash by L. Again, because this is a 90 degree, right? This is angle R. For this is the hypotenuse and this is the perpendicular. Perpendicular by hypotenuse is the value of sine. We are getting d dash by L. Dividing the two equations here, let's name equation 1 and equation 2. Dividing the two equations, we are getting sine I by sine r. Sin I by sine r, we are getting d by d dash and we know that d is nothing but vt, right? This d for the same time d is, we can say, v times t, or suppose that was the time for which it has come to this, and in the same time it has grown from 0 to d dash. So v times t divided by v1t divided by v2t. So cancelling t, we are getting sine I by sine r equals to v1 by v2. Or simply we can say sine I by sine r is equal to speed of light in medium 1 divided by speed of light in medium 2. Is this what Snell's law say? Didn't we discuss this? That mu is nothing but the ratio of the speeds of light between medium through which the light is passing. So this is how Huygens principle can explain reflection and diffraction. I hope you have got it. Do you have any doubt? If you have, please let me know in this session, or in different session I can try to solve that. Now Young's double slit experiment. I'm not sure how much time we have left. So yeah, I think we have only 5 minutes left. We cannot cover the whole Young's double slit experiment, but what I can tell you, Young's double slit experiment was something of this sort. There was one coherent and light source was used, which was emitting a single wave, single frequency light, and an obstacle or a screen was given in front of this, and in the screen there were two slits. You know the meaning of slit, like if you take some paper and make a cut mark into that, that is a slit. So it was something like there was a paper. So why don't I draw it? So this was the paper or the screen, whatever it was, and there was two cut marks here. So in these cut marks light could pass. So this was something like that. There was no rod or something like this. I'm just saying that these were the openings for light. And in front of this there was a screen on which the pattern of light could be observed. So if you see that there is a light and then an obstacle, then you can simply say that the form of light that will form on the pattern of light that will you get on the screen is nothing but again two slits, right? The shape of the slit. But what happened here, there was fringes were formed here, and at the centermost point there was got a bright fringe here, very bright light, then dark light for some duration, then again bright light, then again dark light, bright light, something of this sort. So this fringe pattern compelled people to think about that, and then they came to recall the Huygens principle, and that's how Huygens principle was given that much respect that it owes. So you will come to know more about these concepts in further classes, and there will be more I was supposed to cover wave optics as much as I can, but because of the time constraints I could cover only this much. I hope I could cover more in later classes. Till then, keep learning. Have a great time. Bye.